For any assignment-related queries, call us at +1 678 648 4277. You can mail us at info@mathsassignmenthelp.com, info@mathsassignmenthelp.com, or reach us at https://www.mathsassignmenthelp.com. Problem 1. Modified inner products for column vectors. Consider the inner product x, y equals x asterisk operator by from class, lecture 5.5 notes, where the vectors are in Cn and B is an n times n Hermitian positive definite matrix. A. Show that this inner product satisfies the required properties of inner products from class x, y equals y, x, 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 0 except for x equals 0. Linearity, x, alpha y plus z, equals alpha, x, y, plus x, z, is obvious from linearity the of matrix operations, you need not show it. B. If M is an arbitrary, possibly complex, n times n matrix, define the adjoint M by x, my equals, mx, y for all x, y. In this problem, we use instead of asterisk operator for the adjoint in order to avoid confusion with the conjugate transpose. For this inner product, the adjoint MT is not the conjugate transpose M asterisk operator equals MT. Give an explicit formula for M in terms of M and B. C. Using your formula from above, show that M equals M, i.e., M is self-adjoint / Hermitian for this inner product, if M equals B minus 1A for some A equals A asterisk operator. Problem 2. Finite difference approximations. For this question, you may find it helpful to refer to the notes and readings from Lecture 3. Suppose that we want to compute the operation. mathsassignmenthelp.com. For some smooth function c, x, you can assume C has a convergent Taylor series everywhere. Now, we want to construct a finite difference approximation for A with U, x, on omega equals 0, L, and Dirichlet boundary conditions U, 0 equals U, L equals 0, similar to class, approximating U, M delta x, is almost equal to for M equally spaced points M equals 1, 2, M, U 0 equals plus 1 equals 0, and delta x equals A. Using center difference operations, construct a finite difference approximation for O evaluated at M delta x. Hint, use a centered first derivative evaluated at grid points M plus 0.5, as in class, followed by multiplication by C, followed by another centered first derivative. Do not separate O by the product rule into Cu plus Cu first, as that will make the factorization in part, D, more difficult. B. Show that your finite difference expressions correspond to approximating O by O, where U is the column vector of the M points and A is a real symmetric matrix of the form A equals minus DTCD, give C, and show that D is the same as the first derivative matrix from lecture. mathsassignmenthelp.com. C. In Julia, the diam C command will create a diagonal matrix from a vector C. The function diff1 m equals 1.00s 1 m1 diam 1s m1 1 I m will allow you to create the m plus 1 times m matrix D from class via D equals diff1 m for any given value of m. Using these two commands, construct the matrix A from part D for m equals 100 and L equals 1 and C, x equals E3x via L equals 1m equals 100 D equals diff 1 m dx equals L slash m plus 1 x equals dx asterisk 0.5 dx L hashtag sequence of x values from 0.5 asterisk dx to equals L in steps of dx c equals something from c x hint use diam A equals d asterisk c asterisk d slash dx caret 2. You can now get the eigenvalues and eigenvectors by lambda u equals eig A, where lambda is an array of eigenvalues and u is a matrix whose columns are the corresponding eigenvectors. Notice that all the lambda are 0 since A is negative definite. Using plot dx ldx u colon end 3 end s label x a label eigenfunctions legend fourth third second first. mathsassignmenthelp.com 2. Verify that the first two eigenfunctions are indeed orthogonal with u colon end 1 in Julia, which should be 0 up to round off errors. 3. Verify that you are getting second-order convergence of the eigenvalues. Compute the smallest magnitude eigenvalue lambda m end for m equals 100, 200, 400, 800 and check that the differences are decreasing by roughly a factor of 4, i.e., lambda 100 minus lambda 200 should be about 4 times larger than lambda 200 minus lambda 400, and so on, since doubling the resolution should multiply errors by January 4th. D for c, x equals 1, we saw in class that the eigenfunctions are sin n pi x slash L. How do these compare to the eigenvectors you plotted in the previous part? Try changing c, x, to some other function, note, still needs to be real and 0, and see how different you can make the eigenfunctions from sin n pi x slash L. Is there some feature that always remains similar, no matter how much you change c? Problem 3, Discrete diffusion. In this problem, you will examine thermal conduction in a system of a finite number n of pieces, and then take the n-infinity limit to recover the heat equation. In particular, mathsassignmenthelp.com. You have a metal bar of length L and cross-sectional area A, hence a volume law, with a varying temperature T along the rod. We conceptually subdivide the rod into n, touching, pieces of length delta x equals L slash n. If delta x is small, we can approximate each piece as having a uniform temperature Tn within the piece, n equals 1, 2, n, giving a vector T of n temperatures. Suppose that the rate q, in units of W, at which heat flows across the boundary from piece n to piece n plus 1 is given by q equals where kappa is the metal's thermal conductivity, in units of W slash mk. That is, piece n loses energy at a rate q, and piece n plus 1 gains energy at the same rate, and the heat flows faster across bigger areas, over shorter distances, or for larger temperature differences. Note that q greater than 0 if Tn plus 1 and q less than 0 if Tn plus 1, heat flows from the hotter piece to the cooler piece. If an amount of heat delta Q, in J, flows into a piece, its temperature changes by delta T equals delta Q slash Cax, where C is the specific heat capacity, in J slash kgk, and rho is the density, kg slash m3, of the metal. The rod is insulated, no heat flows out the sides or through the ends. Given these assumptions, you should be able to answer the following. mathsassignmenthelp.com. Newton's law of cooling says that the temperature of an object changes at a rate, k/s, proportional to the temperature difference with its surroundings. Derive the equivalent here. Show that our assumptions above imply that for some constant alpha, for one n less than n. Also give the slightly different equations for n equals 1 and n equals n. B. Write your equation from the previous part in matrix form for some matrix A. C. Let T, X, T be the temperature along the rod.